So we're now going to actually use our trig identities. I think I gave you probably 10 of them a second ago. If you copy those down, perfect. It's nice, but it is on your trig bits sheet. You have these identities on there, so you can refer to the trig bits sheet as well. Okay, so let's take a look at this example. If cosine A equals 3 over 5, let's find cosecant of A. Okay, so going back to your trig bits or your notes, let's take a look. If I have cosine A in my identities, I want to somehow get cosecant A. So I think the best one that we're going to use right now is the unit circle one. Sine squared A plus cosine squared A plus sine squared A equals 1. So there's a little thing I need to tell you. Typically in books and even on the trig bits sheet, and even me, I'm used to saying sine squared theta plus cosine squared theta equals 1. This is more like the universal unit circle. I mean, it doesn't really matter which way you write it because you're adding is commutative, meaning the order doesn't matter. For example, really quickly, 2 plus 3 is the same thing as 3 plus 2. So it doesn't matter which one you use, but this one is more used more often. Okay, so the reason why I knew I wanted to use this identity is because, once again, in all my trig function or trig identities that I've introduced so far, this is the only one that has something to do with cosine and something that kind of has something to do with cosecant. So let's figure this out. I know that cosine A is 3 over 5. So if I plug this in over here, I have to square it because this is cosine squared. And this is equal to 1. And let's just write out the rest. And this is good because now I have one equation with one unknown. So all I need to do is solve for sine squared A. So in this case, we would get sine squared A plus 9 over 25 equals 1. And now let's subtract 9 over 25 on both sides. But we need a common denominator, so let's multiply this 1 by 25 over 25. So on the left side, we really have 25 minus 9, which I think is 16. So 16 over 25 is equal to sine squared A. I'm going to take the square root of both sides. And don't forget, when you take the square root of something, so the square root of 16 is 4, and the square root of 25 is 5. But don't forget, we need to have the plus or minus. And this is equal to sine A right now. Which is good, but remember, I want to solve for cosecant. So what's the relationship between cosecant and sine? Well, they're reciprocals. So basically, cosecant A is equal to 1 over sine of A. So what I'm going to do now is go back to the bottom, and if I want to take the reciprocal of this, well then that would give me cosecant A is equal to plus or minus 5 over 4. Because once again, these are reciprocals of each other. So all I need to do is take the reciprocal of my solution. So now let's do a problem where we're asked to simplify an expression. And remember, this is an expression because there's no equal sign. So to simplify this, basically you just kind of have to play around with it. The way I think about these type of problems is like they're puzzles. You start off with something and then you use your identities to make this, something a little bit neater. So what I mean by that is, if you take a look at your trig bits or in your notes, do you notice any identities that involve cosecant x? Well, yeah, we know by definition, cosecant x is 1 over sine of x. Is there anything that we know that is cosine? Sure we do, but you know what? From my experience, I know that I want to keep this as just cosine x. Is there any other way that we can rewrite cotangent? Yes, in our trig bits, I think we can rewrite cotangent as cosine x over sine x. And then check this out. The sine, 1 over sine is still 1 over sine. There's nothing I can do there. But I can multiply these two fractions. And to multiply fractions, all I need to do is multiply across. So cosine times cosine is really cosine squared. The denominator is still sine x. And hey, and this is even nicer because I have two fractions where I'm subtracting it and I have a common denominator. So really this is the same thing as 1 minus cosine squared x over sine of x. Now go back to your trig bits. Do you see any identities that has like a 1 and a cosine squared in it? So is there something that has both of those properties? Yes, it's our original unit circle. So what I mean by that is we can manipulate this blue equation to look like my 1 minus cosine squared x. And we can do that by subtracting cosine squared x on both sides. So what we get is sine squared x equals 1 minus cosine squared x. So what does that mean? That means I can replace my numerator with sine squared x. So now we have sine squared x divided by sine. And hey, sine squared is really just sine x times sine x. And if we're dividing out by sine x, doesn't that mean that we can cancel the denominator with something in the numerator? So our final simplified solution is sine x. And hey, yeah, that totally works. In this example, we're asked to simplify sine squared x plus sine squared x times tangent squared x. So here's the thing. I've been doing these type of problems since I was in high school. So I'm really comfortable and know how to manipulate these. So don't get boggled down if you don't see it right away. You'll get used to it and you'll eventually be able to play around with it a little bit more. Okay, so I know right now that this is an addition problem with a product in there somewhere. But you know what I noticed? I noticed that I have sine squared x in both of these terms. So you know what I'm going to do? I'm going to factor out the sine squared x. So if I factor out sine squared x from this term, what do we have? 1. If I factor out a sine squared x from this term, what do we have left? Tangent squared x. And now, if you take a look, is there any trig identity that has 1 plus tangent squared x? Actually, yes, it's one of the unit circles. We know that this is equal to secant squared x. And we still have this sine squared x out here. And I think we can simplify this even more because secant squared x is the same thing as 1 over cosine squared x. And we still have this sine squared x. Haven't done much there. But I noticed that this is kind of like two fractions, so I'm going to just multiply across. So we get sine squared x divided by cosine squared x. And hey, what does that look like? Where else have we seen sine divide by cosine? Well, that's just tangent. But it's not just tangent because I'm squaring both sine and cosine, therefore it's tangent squared theta. Or not theta, but tangent squared x. So notice I've simplified this expression to look like tangent squared x. So once again, my advice when you do these type of problems is don't be scared. You just have to play with it, just plug things in, see if anything comes out. And if you make a mistake, it's okay. That's why God made erasers.